Good morning everyone, good morning all the students. How are you all? I'm also fine. This is Prema here. This is my channel SciMa Academy, and today I'll be starting up with the science chapter. Okay, so I'll be taking up the structure of atom, which is one of the most important chapters of grade 9 chemistry. And I found that from my students and other students, I found that this chapter is little tough for them. They are finding it little tough to understand. So that's why I chose this chapter to explain it to you. Okay, so take your notebook and your pen, and you can pause the video in between to take up the notes, because I'll be presenting the video, I'll be explaining. At the same time, simultaneously, you will be taking up the notes also. This will help you in your exam preparations, okay, as exam is nearing, and you can make notes also out of it. Okay, so don't forget to subscribe to my channel, that is SciMa Academy. I'll be coming up with more videos in front of you. So let's start with the chapter. Now there was a revolutionary experiment given by Rutherford. Okay, so Ernest Rutherford, as you can see here, in 1871 to 1937. So he is known as the father of nuclear physics. So he gave an experiment. Okay, he designed an experiment to understand how the electrons are arranged, how the electrons are arranged in an atom, and what does an atom contain. So he was the one who actually discovered nucleus also. So he received also Nobel Prize in chemistry for his work in nuclear structure and radioactivity. Okay, so this is the setup, if you can see here, and this is the setup. What is the experimental setup here? What he used fast moving alpha particles. Now what are alpha particles? Alpha particles are doubly charged, or you can write they are doubly charged with 4 unit of atomic mass. Okay, so alpha particles are doubly charged helium ions. Okay, sorry, they are doubly charged helium ions. Okay, so these alpha particles were actually made to pass through the gold foil. Now why this gold foil is used? Very thin sheet of gold foil is used. Okay, now why gold foil is used? You know that gold is a metal, okay, and it is malleable, right? So malleable means, what is malleability? It is a property of a metal where it can be hammered into thin sheets. Okay, and why we need thin sheets of gold foil? Because when alpha particles are hitting on that, when alpha particles are passing on that, so alpha particles will pass only through few atoms. We don't want it to pass through more atoms, okay, of gold, and for here we prevent the alpha particles getting absorbed also. So that's why we need a very thin sheet of gold foil, which will help the alpha particles to pass through without getting absorbed. Okay, so here in this experiment, alpha particles were made to from the source, alpha particles were made to pass through the gold foil. Then what you see, okay, what the detector, this is a detector, what it is detecting, like how the alpha particles, what is the nature of movement of the alpha particles, okay, is seen from this experiment. So the experiment setup was fast moving alpha particles were directed at thin gold foil, which is 1000 atoms thick. Okay, now alpha particles are what I told you, they are doubly charged helium ions, okay, and mass of 4 units. Okay, and they have considerably more energy, and they show minimal deflection. Okay, so they will not show minimal deflection because they are heavier than the protons, because it's helium, doubly charged helium, so it is little heavier than the protons. So we expect in this result alpha particles were chosen because so that it doesn't show much deflection. That was they thought that it is not going to show much deflection. That's why they selected alpha particles for this experiment. Okay, so now what was the observation? So now if you see, this is an atom, so it is passing through the gold foil. Now gold foil, we have large empty space, and here you have electrons here and there. Okay, now alpha particles are positively charged, right? So what was the observation? Most fast moving alpha particles passed straight. They passed straight. If you see here, this is passing straight, here also passing straight, here also passing straight. So most of the alpha particles, if you see, they are passing straight through the gold foil. Okay, and some alpha particles were deflected by small angles. See here, some are deflected by a small angle here, some are deflected by a small angle here, right? So some are deflected with smaller angles, and out of every 12,000 particles rebound. Now what is rebounding now? Rebounding means going straight and taking a turn, 180-degree turn. Okay, that's just coming back. That is called rebounding. So if you see, 1 out of 12,000 particles means very few particles actually took a 180-degree turn. They just rebounded straight back. Okay, so very few rebounded like that, but most of the alpha particles, they just went straight. As you can see here also, if you can see here also, you see many are passing straight, right? Straight. Some went by some angle. Okay, some passed by some angle, right? But some took a rebound. Very few you see that they came back 180 degrees. Okay, so most alpha particles pass through undeflected. That means many have gone straight, many went straight, and some were slightly deflected, and very few were deflected with 180-degree deflection, like they went straight back. Okay, so that was his observation when he conducted this experiment. These were the 3 observations he found. Now what was the result? Now what was the conclusion he drew from this experiment was that this is a conclusion part. Okay, the conclusion of his experiment was most of the alpha particles passed through undeflected, proving, now if most of the particles are, so now see, most of the alpha particles are just going straight. Okay, if this is the central core of the gold atom, so here most of them are going straight, which what it suggests, if most of the alpha particles are just passing straight without getting any obstruction, that means we can say that atoms are empty. Most of the atom space is empty space. Okay, that was one conclusion. Second conclusion, few deflections indicated positive charge occupies very little space. Okay, so some were deflected. Now some were deflected, only little were deflected, right? So here is what present here, electrons are present. Okay, so some, when the alpha particles are parting, they are deflected by small angles. Okay, so what he concluded from that, the few deflections, the less number of deflections which he saw indicated that the positive charge occupies very little space. That means here positive charges are very less. Okay, because here there is attraction from the negative electrons, right? Because this is positively charged alpha particles, right? So here, because of that, deflection is seen, but which suggests that the positive charges are very less in the empty space. Now where are these positive charge? Now that was the question. And he said also that dense nucleus, 180-degree deflection revealed that all positive charge, so when the 180-degree deflection took place, now here when it is passing here, it is coming back at 180 degrees straight. Okay, so that is the rebound which is happening. So which made him conclude that the mass of the nucleus, mass of an atom is concentrated, or the positive charge of an atom is concentrated in a very small space. Okay, here at the center only, very small space it occupies. Okay, so he says that the nucleus is dense. This is the nucleus. He was the one who actually discovered nucleus, which is positively charged because of protons. Okay, and he said that the nucleus is very small part of an atom, and rest of the part of the atom is actually empty. So rest part, if you see, electrons are here, and it is most of the part is empty, and the main positive part is actually in the nucleus. So he said that 180-degree deflection revealed all positive charge and mass concentrated in tiny nucleus. So nucleus is very small part of the whole atom. Okay, so what were the key features? Now the key features of the nuclear model was positively charged center. That is, nucleus at the atom center contains nearly all the atomic mass. So the atomic mass is, now I told you that mass of a proton is 2000 times that of electron. So electron's mass is considered as negligible, nil. Okay, so where is the mass of the atom concentrated now? If the protons are present in the nucleus, the whole mass of the atom is concentrated in the nucleus only. Okay, so that was his key feature. Nucleus nucleus at the atom center nearly all the atomic mass. So whatever atomic mass is concentrated in the center of the atom, okay, that is in the nucleus. And electron revolution, electrons revolve around the nucleus in circular path. And he also said that electrons, now if you see here, electrons are, he said that electrons are revolving around, so electrons revolve around the nucleus in circular path. So if this is the nucleus, you see here, this is the nucleus with this, which is positively charged, and electrons are revolving around it in a particular way, okay, it is revolving around the nucleus. That's what he's saying. Okay, that was about the electrons, he said. And size comparison, and he said that nuclear radius is about 10 power 5 times smaller than atomic radius. That means it is very, very small part of the atom. Okay, nucleus is a very tiny part of an atom. If atom is so big, nucleus will be very tiny part of the atom. Okay, so these were the key features of nuclear model. This was the conclusion of the experiment. These are the key features. Okay, so these were the experiment conducted by Rutherford, but there was a drawback also. Okay, so as I told you now, Rutherford said that the mass is present in the nucleus, positive charge is here in the nucleus, and electrons are revolving around it. Now what happens when the electrons are revolving around it? Now see, if you see, this is the positive part, okay, this is the nucleus, right, this is the nucleus, and electrons are revolving around the nucleus. So if you see, so if this is the nucleus, positively charged, and I say electrons are revolving around it, right, in a particular way, it is revolving around it. So what happens now, what was the drawback of Rutherford's model was that, see, when the electron is revolving around the nucleus, because it is revolving, it is in motion, right? So when it is motion, it is having some accelerated motion, right? So when a body is moving in an accelerated motion, it always loses energy, okay, it always radiates energy. Okay, so this is the electrons which is moving will radiate some energy, right? Ultimately what will happen, it will lose all the energy and it will fall back onto the nucleus. Okay, so that was a drawback Rutherford could not explain. So Rutherford's model faced a problem, that is, any charged particle in circular orbit undergoes acceleration, okay, and it will radiate energy. So when it is radiating energy, what will happen? Revolving electron, as it is moving into the spiral orbit, okay, so what will say? It will lose energy and finally it will fall onto the nucleus. So in that condition, what we can say, that atom is unstable. The atom becomes unstable when the electron is falling back onto the nucleus. As such, we say atom will be unstable. Okay, so that was something which Rutherford failed to explain, okay, about how the electrons are revolving around the nucleus. Okay, this drawback actually was explained later by Bohr, which we will study in the next atomic structure of atom. Okay.